Hi, and welcome to a video on more about power series for our Calc 2 class. And we should have just completed a section on power series and those interval of convergence and radius of convergence associated with such power series and using, the ratio test to determine that. So just kind of a quick recap here. If I'm looking at this power series, that is that infinite series, it's also geometric, right, where we talk about your common ratio, in this case being 1x. And so because it's geometric, I can actually find the sum of the series. And so if you'll remember, the sum of a geometric series was our first term over 1 minus that common ratio. So my sum in this case would be my first term, which is 1 over 1 minus the common ratio of x. So what I'm in essence saying is the series of 1 plus x squared plus x cubed plus dot dot dot. So this series starting at 0 going to infinity of all x to the n. So that power series has a sum of 1 over 1 minus x. And so if I wanted a way to rewrite or change the form of 1 over 1 minus x, I could turn it into this infinite power series, and that is going to make our life easier. Maybe not necessarily for a 1 over 1 minus x type case, although I would agree, I still think it's easier. But maybe, for example, like sine of x, I can turn that into a power series as well. So we talked about in the last video on interval of convergence, finding that interval of convergence, and we found that based on the ratio test. And in this example, I can see that I will converge if that absolute value of x is less than 1, or if it's between -1 and 1. Because it was geometric series, I know that I do not converge when it equals 1, so I don't have to test the endpoints. And we said that that radius of convergence was 1. So that should give us kind of a beginnings or basic idea on some of these power series. Now, there's a whole bunch of these power series, so let me show you some of these that are written out already for you. Okay, so here's an example of a sheet that if you're in my class, I will make accessible to you. This is some of the examples of some of the different power series that we're going to look at. So if you look at the very first one there that's written, that is a series that we are talking about. So that is the series of 1 over 1 minus x being this infinite power series right here. We also have a series for 1 over 1 plus x, right? There's our power series to represent that function. E to the x, sine of x, cosine of x, natural log, inverse tangent, etc. So we have these power series that we can then be using, as well as their radius of convergence off to the right. Okay? So again, if you're in my course, I'll make that form accessible to you. If not, it's probably in your textbook of whatever you are learning from, or you can Google it. I'm sure there's some online. So in this section, we're going to be talking about how to make a new series from an old one. So you're going to be basing your series off of something that is on that paper. We will actually formulate, using the definition of Taylor series and Maclaurin series in the next video, how to come up with these series on our own. From now, we're just taking one that we already know and making a new one. So suppose I want to find the power series which represents 1 over 1 minus x squared and its new interval of convergence if it has changed. We can use the series above to do that. So all I'm going to do is compare how does 1 over 1 minus x squared differ from 1 over 1 minus x, and that is because of a substitution. So if I substitute x squared in for x, I will have my new series. So for example, 1 over 1 minus x squared is going to be equal to 1 plus, I'm substituting in x squared in for x. So this is now x squared. I don't need the parentheses there, but just bear with me here. plus the quantity x squared squared. Do it again, plus the quantity x squared cubed plus dot, dot, dot. Now here's the really neat part. Go to your summation. You don't have to reinvent the wheel and figure out this pattern on your own. You're again substituting in x squared for x. So this is x squared to the n. And again, you can write this out if you want to differently. So this is 1 plus x squared plus x to the fourth plus x to the sixth, dot, dot, dot. And then you can write your summation out more clearly. So it's the sum from 0 to infinity of x to the 2n. So this is my new power series that will represent that rational function. And just make sure that you do, in fact, get that first term. So if I put 0 in for n, I get x to the 0, which is indeed 1, and you can test terms all along the way. So how can I find my new interval or radius of convergence? Well, we can use the ratio test anytime we want to see or prove to ourselves if that interval or radius has changed. This was the starting interval with a starting radius of convergence of 1. And I haven't actually shifted, if you know transformations, I haven't actually multiplied my x by anything or added or subtracted anything to x to shift over my center, so to speak. So I haven't actually changed my interval of convergence, but the ratio test shows what that would be. So we can find all kinds of new series just by adjusting these old ones, okay? So we're going to find the power series and the interval of convergence for the following. All right, so if I'm looking at 1 over 1 plus x squared, now what I'm going to look at is I'm going to start with a different series. I'm going to actually start with the one that is 1 over 1 plus x. So I've written that one out. Again, you should have that as a resource to you. I'm not expecting you to memorize that yet. We'll be able to derive that here soon because this is just the geometric series. But we're going to substitute in x squared in place of x. Okay, so I have 1 over 1 plus x squared. And again, I'm substituting, so I will use parentheses so that I'm accurate. So 1 minus x, which is now x squared, plus it's x squared squared, minus x squared cubed, plus, I'll do 2 more, x squared to the fourth, and then minus that x, which is x squared to the fifth, plus dot, dot, dot. Again, that's the important part, right? These are infinite series. And here's my summation notation or power series. This is the sum from 0 to infinity. Negative 1 to the n should not be changing here. But instead of x, you are substituting in x squared. I can certainly leave it like that, or I could rewrite that piece of it to be x to the 2n. And again, if I wanted to look at these terms and see them a little bit more simplified, I could do that. Again, you're multiplying those powers. And at any time along the way, you should be able to check when n equals 0, do I get that first term? Is this n equals 1? And so forth, and it is. So I really haven't changed my interval of convergence, although if you're unsure, the ratio test can prove that to you, and so my radius of convergence is also 1. Okay? When they ask for a power series, they're usually looking for this power series in summation notation. If they wanted you to write out the first few terms, they'll usually ask for that. All right, now here's one that's not quite as intuitive, and I wanted to go through a couple rewrites here just so you can kind of see this, and then we'll do another one here in a minute. If I'm looking at the series 1 over x plus 2, I want to be able to use this series right here. So I want to be able to use the series 1 over 1 plus x. Now, we can substitute anything we want in place of x. I can substitute in 3x or x over 2 or x squared, but I can't change the fact that it's supposed to start 1 plus x, okay? So if that's the case, that's why I needed to factor out the 2, because this is really 2 plus x in the denominator, and I want that to say 1 plus. And again, I can substitute anything else in for x that I want. So when I factor the 2 out of the denominator, or really I'm factoring out a 1/2 from my whole summation here, it would be 1 over 1 plus x over 2. So this r has now changed, so I probably should go through ratio test to find a new interval of convergence. Okay, so if we think of this as first term over 1 minus the rate, like a geometric series would look like, or you'll see when I write these out, you'll see the change in r, and I know it will converge if that r is between -1 and 1, and so that's how I found my new interval of convergence. So if I'm starting from this blue highlighted series here, I first of all am going to have a 1/2 in front of everything. Okay, so there's my half in front of my whole summation notation, power series, and in front of each of the expanded terms. And then if I look at each term in between, this x over 2 does now get substituted for x. Okay, so that's why you'll see instead of x, here's x over 2, here's x over 2 quantity squared, here's x over 2 quantity cubed, and so forth. And then in my power series, instead of x, gets put x over 2. Now we're going to be going to the point where we're differentiating and integrating these series, of course, because we're in calculus, right? So I don't necessarily want to see x over 2 as a quantity, because then I'm going to have to use substitution or chain rule, depending on if I'm differentiating or anti-differentiating. So I like to see these separated out. So what I like to see is this is x to the n over 2 to the n separately. Because again, n is 0 and then 1 and then 2. When we're talking about differentiating or integrating, it's usually with respect to x. So n, again, I know what n is going to be, 0, 1, 2, 3, all the way to infinity. Well, then I can combine it with that 2. So that's why I kind of put that dotted line over there. And that's how I get this nice, neat, concise summation notation or power series, and that's probably what I would want to work from. And then again, we talked about that interval of convergence because I can see my common ratio each time is that x over 2, and so that needs to be less than 1 as absolute value, or between -1 and 1. So my new interval of convergence is from -2 to 2, and that radius of convergence then would be a 2. So that's kind of a commonly missed one, only because people don't think that that 2 plus x is a big idea, and they kind of glaze over it or factor out the 1/2 without factoring it out of that x. So we've got to be careful about that. So number 3 is going along the same lines as number 2 here. So number 3 is the same series as number 2, but it is multiplied by 3x cubed. Okay, so I can take each term along the way and I can multiply by 3x cubed. So I have 3x cubed times all of this that I'll highlight up here, that I'm going to write down. All of this, okay? So it's 3x cubed times, it's the 1/2 times 1 minus x over 2 minus x squared, plus x squared over 4 minus x cubed over 8, etc., plus dot, 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 right? Or it's 3x cubed times this summation. And I'm going to put that into my summation so you can see that. Okay, so 3x cubed times this -1 to the n, I'm going to use this bottom one down here, times x to the n, all over 2 to the n plus 1. And so my power series, I'll leave the 3 again separate because I don't want to mess that one up. So it's 3, -1 to the n. Then this, you have x to the third and x to the n. That is not x to the 3n. Be very, very careful because this is x to the n plus 3 all over 2 to the n plus 1. So there is my power series. And then my interval of convergence, or IOC, is still negative 2 to 2. Oops, parentheses, excuse me. And the radius of convergence is still 2. And again, I can use ratio test to show that if I wanted. Okay, last example here before we get into sort of how this works in real life scenario and differentiation and integration of these power series is if this is the power series that I'm working with, I see a product in the denominator, and when I look through that list, there is not necessarily a known series with that product in the denominator. So what I'm hoping to do is find two series where I can add or subtract those two series together and then determine my power series from that way. So how do I turn one fraction into two? And hopefully we know the answer to that, which is partial fraction decomposition. So partial fraction decomposition. So here's yet another example of your applications of partial fractions. So I'm going to kind of take this aside here and say 1 over x minus 1, the quantity x minus 3. Okay, so this equals, I'll just say a over x minus 1 plus b over x minus 3. And when there's only two fractions and they're linear, this shouldn't take you too long to figure out that it's 1 equals a times the quantity x plus 3 plus b times the quantity x minus 1. I will distribute that because I will equate the coefficients. That's the method for these that I think will go the quickest. So I have a plus b, those are my x's, and those need to add to 0 because I have 0x on the left. And then my constants are negative 3a minus b, and those should add to 1. And so what I see is now adding down, I have negative 2a is 1, so a is negative 1/2. And so if I put that back in, b is positive 1/2. And so if I just rewrite this from the beginning, it would be negative 1/2 over, my a was over x minus 1, make sure you're getting that part right, and the b, which is 1/2, is over x minus 3. And that seems to be better. I can certainly rewrite this again if I wanted to and say that it's negative 1/2 times 1 over x minus 1. That might help me. And 1/2 times the quantity 1 over x minus 3. Again, that might help me. But I have down here a known series that I want to work from. So if I know that series and I want to work from this series, I have a little bit of work to do still to get my series, each of them, ready to look like this. Now remember, I don't necessarily care about that x, if it's positive x or negative x, or if it's x over 2 or x over 3. That's not the piece or component I care about, but this starting constant needs to be 1. And so if I just rewrite this in the same order, and I just look at what does this even look like from that perspective. All right, so if I just rewrite this, I get negative 1/2, and then I have 1 over, this would be negative 1 plus x, just so I can see my constant first. And so I do want to factor out that negative. So if I factor out that negative just from the first term, I'll get positive 1/2, 1 over, and if I factored out the negative, again, I put it out front of the whole fraction, but this would be a positive 1 and a negative x. So now that's ready to use my known series. And then this other one, though, if I rewrite it in the appropriate order, I have 1 over negative 3 plus x. And again, that negative 3 can't be negative 3. So I'm going to factor out, right, that negative 3. And so I have minus 1/6, 1 over, and again, I'm factoring out negative 3, so that's a positive x, and this is now negative x over 3. Again, I can substitute in an x over 3 instead of x, that is fine, but I can't change the constant for that series that I know. So now if I know this series, okay, if I know that series, and that is the work that I just did, it's just kind of repeated over here so I can get there. And I know this is the power series, right, x to the n. This one is the exact series, it's just multiplied by a half, no problem. This one, I'm going to substitute in x over 3 instead of x. And then I have, of course, that 1/6, and the minus is just in front of that summation. And so I just write this as one summation instead of two, because they're both starting at 0, they're both going to infinity. And so if I look at this one first, the one on the right, this is 1/6 times x to the n over 3 to the n. And so I can separate that out, right? Because I can say this is x to the n over 6 times 3 to the n. And so when I factor out an x to the n from both series, right, here's my x to the n that I'm going to factor out of both series. I have a 1/2 left in the first series, and then this 1 over 6 times 3 to the n in the second series. And then again, I can use the ratio test if I wanted to show this, what my interval of convergence will be, and it is still going to be a -1 to 1. So again, this is just sort of the first part in a two-part series on how to make a new series from an old one. Again, assuming that these old series, so I'll call them old series for lack of better terms because we're making a new one, assuming that these old ones per se are known. And then we'll talk in the future about how to create these series using the definition of Taylor series and Maclaurin series on our own. But the very next video that you're going to find is how to differentiate and integrate power series. So that's part 2 of this two-part series, I guess. Thanks for watching.